So number 91 gives us a couple of pieces of information, and I apologize for this being blurry, but it gives us a value of a product in 2009. So in 2009, the value of this product is $20,400. And then it says the rate at which the value of the product is expected to change. So the rate of the product is increase or decrease per year. Information. What can you try to information? So how can I take information from the equation?
Why did 2000 as M?
Did you use it, Peter?
Because it's decreasing.
Yeah, so rate of change, the annual rate of change, the slope, the rate of change in application problem. The slope is more just equals a graph. It really applies to information or a result. So we said the slope is negative 2000. All right, do.
In the y-intercept, I guess I could have plugged in 20,400, but instead of that, I multiplied the negative 2,000 by 9 because you need to find what it was at the beginning. And then I subtracted that from the value of 2009.
Which is actually exactly what you were just saying. You were just doing it more logically at using the equation.
Yeah.
So in this problem says let t equal 9 represent 2009. So if we know the value is 20,400, and that value happens when time is 9, and plug in, which is exactly what Peter did. He just didn't use the equation. He was still finding the y-intercept. So knowing that 9 represents the value, when I multiply 2,000 with negative 2, I get negative 18,000 to the other side. And then, Peter, what did you get for the b value? The original value?
For the b value, I got 38,400.
Yeah. So remember, y-intercept is value. So we're talking about the year 2009, but the original would have been 38,400. So that would be our y-intercept. To give us, and realize that 2009 is the y-intercept, but instead it's a 9th year of this product that we'd be purchasing, and that's the value of it for 9 years. So we can figure out y-intercept by putting in the 9 in the value and then solving for b. So now we have an equation. We knew the slope was negative 2,000. It's decreasing after time, which is why the value of our object to begin with, or our product to begin with, is more than 9 years later, because it's $2,000 every year. Any questions with 91? And you would do it the same way. You plug in the 9 and that the product is worth in the year 2009. But it's understanding that the number they give you is of the problem, the y-intercept. So then the other pair of problems people asked was 101. When 201, we could do 105. This one, when you use a graphing calculator to graph the equation that would be in the form x over plus y over b equals 1. And then it says use the graph to make a conjecture of what you represent, and then it says verify your conjecture. If you look at 101, they're asked to kind of think about equation if you're going to use the graphing calculator.
Put it in y equals format.
Yeah, put it in y equals 4. So we have x over 5 plus y over negative 1. We have this equation in 1 to plug in the calculator. So do you know how we can take the fractions out of the equation?
First, would you want to move at the other side?
So we have y over negative. Moving x over 5, it becomes negative, because our goal is to get y by itself. So we'll take the over. And then we'll
multiply by negative 3.
Multiply by 3 on both sides. That definitely works. Multiply by negative 3, negative 3. So that gives a positive 3/5 x, and then a minus 3. Okay, so now I have this equation. Yes, you can plug this calculator, but I'm not going to because, one, I have to change screens and that's just too much. But another reason, I don't need a calculator to see if I can try and find out some information about the graph. So if I look at this equation, and I'm trying to think about x and y, what's the y-intercept in this problem?
Negative 3.
Negative 3. So the y-intercept is negative 3. That's an important part. So if I were graphing this, I would graph it at a y-intercept of negative 3. Well, I can do that without using a calculator because I know that it starts at negative 3. Darby, what's the slope of this problem?
Positive 3/5.
Positive 3/5. So again, I know that I don't need a calculator to graph a line. I can go up 3 and over 5, and now I have a line. Way easier for me right now than flipping a screen and sharing another screen going to the calculator. So we have a y-intercept and we have a slope. This question is asking you to make a conjecture, an educated guess about what the a and the b value represent. Well, those are the two values in the bottom of the fraction. So if you look at my graph and the 2 points that I have plotted on this graph, what does it look like the a and the b value on the bottom of the fractions would represent?
They'd represent x and y.
Yeah, they'd represent the x and the y intercepts. So the a value represents the x-intercept because look, this x-intercept is at 5, 0. Well, right there is my a. It's underneath x. The b value represents the y-intercept. And again, it's right there at 0, -3. So a is the x-intercept, b is the y-intercept. It's kind of neat how that pairs together. At least in my mind, I think it's neat. So then if I take this and extend it to the next problem, it says write the equation of a line that passes through the points. Well, I'm trying to use the result that we found in the previous problem. So taking the previous equation, x over a plus y over b equals 1. Now knowing that the x-intercept is the a value, I could say my equation would be x over 2. The y-intercept is the b value. And now I have an equation of a line using the information that we found from the previous question. So now, yes, you could change the form of this equation of the line just like Joe did for the last problem. We could get y by itself. We could get slope-intercept form. I could get standard form. But this is using the previous question and kind of understanding what that a and b represent. Once I have those intercepts, I can plug them in for the a and the b value. Questions? So the trickiest part, I think, getting started was recognizing that you have to take the equation of the line that's given and try and get y by itself so that you can actually graph it. And then just looking at what do the information from the numbers from the equation, how does that correlate with the values that were given in our line? And it directly correlates with the x and the y intercepts. Any questions? Okay, so today, as I said, we're going to look at functions. So in your notes packet, we are looking at section 1.2. This will be page 6 in your packet. And this is all about functions. And this is more of the algebraic approach to the function than the graphical approach. We'll do the graphical approach in the next section. So the first thing we have here is just kind of a refresher of the definition of a function, which was chapter 2 from last year. So thinking back from last year, we talked about many different types of functions, but why were the equations that we worked with functions? What was special about it that made it a function? So what makes an equation or a relation a function? Jack, do you remember why an equation or a relation is considered a function?
Because every x only has one y, or every input has only one output.
Yeah, perfect. I like that you use both words. So it's a relation. A relation is a mapping or a pairing of x and y. Sometimes we call it a correspondence as well, like pairing x and y together. So a relation, as he said, where each x value, he also used the word input.
You're where twice.
Thanks, Jack. And then what did you say about the x value, Jack? Or the input?
Every input only has one output.
So a relation, a specific relation where each input or each x value has only one, exactly one y value or output. And that one is key. So only one, exactly one. It cannot have more than one. So a relation can be as simple as a set of points. A relation can represent an equation. Just a really basic example. If I have a relation can simply be a set of points. So mapping x and y together. So that is considered a relation. Points, relation, pairing x and y. Jack, based off of your definition, would the example that I have be a function?
No, because 3 gives 2 and also 6.
Yeah. So the x value or the input of 3 is paired with 2, and then it's also paired with 6. So it's not a function. So the x value of 3 has 2 output values or 2 y values. That means it's not a function. I could create another one. I could still use 0, 1, negative 5, 4, 3, 2, but maybe change it to 6, 6. Then it is a function because each x has exactly one y. So a function exists when each x is paired with one y value. So that's just looking at it as a simple set of points. However, we can look at it in equation form as well and trying to decide if an equation is a function. So in example 1, it says, is y a function of x? And that's generally how you're going to be kind of stating it. X is usually the value that's the independent variable. Y depends on x. So y is a function of x. We have two equations here that we're going to try and decide if one is a function or if one isn't a function. Maybe they're both functions. We have x equals y squared, for example, A. Now, the question says, is y a function of x? Right now, this is written as x equals y squared. Jeremy, what do you think we should do with this equation, x equals y squared?
Square root it.
Yeah, why would we want to do that?
You get the y by itself.
Right. We're trying to show, is y a function of x? So we need to get y by itself. So I'm going to flip-flop it as well and place the y on the other side. Jeremy, when you take a square root to solve for something that's squared, what do we have to remember about that, doing that process?
It can be positive or negative.
It can be positive or negative. Don't forget that. When you apply a square root to a problem because you're solving for something that was squared, it can be a positive or negative output value. So that means, just kind of getting you to think a little bit, if I plug in, we'll say a 4 for x, or a 9 for x. Jeremy, what would my output value be if I plugged a 4 in for x?
+2 or -2.
And if I plugged a 9 in, I would have?
+3 or -3.
So is y equals plus or minus square root of x a function, Jeremy?
Yeah.
Why?
Because an x value No, it's not a function.
Why isn't it a function? Why is it not a function?
Because an x can't have two y values.
And x can't have two y values. And that's what the plus or minus means. So this is saying I have a point at 4, 2, and I have a point at 4, negative 2. My 1x has two y's. So because of that plus or minus, it's not a function. Any x I plug in is going to have two y answers, because to get y by itself, we had to apply the square root, which means I applied the square root to the equation, I get a plus or minus. So looking at B, these two equations were given because this is a very common misconception. If I look at B, I have the square root of x plus 5. The square root is already in the equation. It's given to us. We didn't solve to get y by itself. So that means the only sign that goes in front of here is a plus, or the given value in the original equation. If I have a little t-chart again, just to get you to think a little bit here, and I make, we'll go with 4 here, and maybe a negative 1. Jenny, if we plug a 4 in for x into this equation, the square root of x plus 5, what would our y value be?
A 3, a plus or minus 3.
It's only going to be a plus.
Oh, that's right.
3, because the plus is the symbol that's technically in front of the square root, because the square root was already in the problem. I didn't apply it to the problem to solve for a y squared. It was given to us. So it's just a plus answer. Jenny, what happens if we plug in a negative 1?
You would get 2.
You'd get a 2. So each x has one y. That means this one is a function. And this would be the most common misconception of functions in pre-calc that I see from students. So you have to understand that if the symbol is already in the equation, the square root's already given to you, the answer is only a plus answer. Because this graph, if I look at the graph of a square root, it's that hook graph. A radical graph just hooks to the positive direction because it has to have the positive values. So that's why it's a function. It's just that positive graph. Where part A, it has the plus and the minus. So now I have two answers for each x. So write yourself a little note to get you to remember that when you solve for something that was squared and you put the square root into the equation, it's plus or minus. But if it's given to you in the equation, then it's just the plus symbol, or if it had a minus symbol in front of it. It's just the symbol that appears in front of the radical. Questions with that? So we do have a way to notate if an equation is a function. Function notation is that f parentheses x. Once I know it's a function, then I replace y with f of x. So remember, we read this as f of x. So I know it's a function, then I can say f of x equals the square root of x plus 5. I could take the y out and replace it with f of x. For letter A, I can't do that because it's not a function. So function notation, once you're using function notation, you're saying it's a function, that relation or the equation you are given. Any questions? All right, we're going to now try and do the applying part. So we've talked about it is a function. In example 2, we have the volume with respect to the radius. So V of R, volume of a radius, or with respect to the radius, is 4/3 pi r cubed. Anybody know what this volume is for? 4/3 pi r cubed? A little bit of geometry.
Isn't it for a cone?
A cone?
I thought it was a sphere.
How about a sphere? Yeah, you were on the right track. You knew that it had to have some kind of circle part in it. So this is a sphere. 4/3 pi r cubed is the volume of a sphere. It says to evaluate. So A has V of 3. Remember, whatever's in parentheses represents the independent variable in our equation, our function. So that means we're going to take our function and we're going to replace r with the value of 3. So we have 4/3, we have a pi, and then we have r, which is now 3, and it's cubed. Now, I don't want you to get out that calculator and plug pi into your calculator. We're going to try and keep these numbers exact and not get decimals. So we'll try and do everything as exact as possible. 3 cubed is 27. So now I'm taking 4/3 times pi times 27. And I still don't want you to grab that calculator. If I have 4/3 times 27, remember I can reduce. The 3 goes into 27 9 times. And now when I multiply, I have 4 times 9, which is 36. And then I'm just going to keep the pi in the answer. So this becomes 36 pi. So my radius is 3. The volume of this sphere with a radius of 3 would be 36 pi. Questions? So you can reduce fractions like that, just like we did reducing fractions when we were looking at rationals. All right, my second one says the volume and then in parentheses 2r. Well, whatever is in parentheses has to replace r, all of it. So my equation or relation, my function says 4/3 pi, and then I have 2r, and that's cubed. So again, I have 4/3 pi. Does anybody know what 2r cubed is? So what happens when you have 2r and you cube it?
Would it be 8r cubed?
Yeah, nice, Peter. So you're cubing the 2 and you're cubing the r. Both of them are in parentheses, so I have to cube both of them. All right, when I go to multiply this one, I can't cancel 8 and 3 because they don't reduce at all. So I'm just going to multiply the two numbers in the numerator together. That's 32. I have the 3 in the denominator, so 32/3, and then I'm going to write pi r cubed next to it. So my volume would be 32/3 pi r cubed. Whatever the radius is, it still has to be cubed. Essentially, I took the 2 value and we kind of like made everything double. We doubled the radius value, but it had to be cubed first because that radius value is cubed. So I want you to keep the pi in the problem. We have the r cubed in the problem because I didn't have a number to replace. Questions? All right, there's one more here. Again, looking with the fraction, I want you to try and do this without a calculator. So we have 3 halves. We're plugging in we have 4/3 pi. R is 3 halves, and we're cubing that. You can easily cube a fraction without using a calculator. You do the top, you do the bottom. Cube the number on the top, cube the number on the bottom. So if I cube 3, I get 27. If I cube 2, I get 8. So now I do a little bit of canceling because I don't want you to rely on that calculator. You're too dependent on the calculator, and we don't need to be dependent on the calculator. So I can reduce 3 and 27. 27 becomes 9. I can reduce 4 and 8 becomes 2. And again, the reason I can reduce these is because it's like cross-diagonal canceling. What's in the numerator can cancel with something in the denominator. So what we have left is 9 halves pi. Questions on any of those evaluating steps? Because we're going to now go into that application process. All right, so here's the big example for today. This is the new thing. You're given an equation, and that equation is a quadratic. We have x squared minus 4x plus 7. We're using the function information, so we're going to use exactly what we did above. But we're going to find this crazy looking function where it says f of x plus h minus f of x all over h. This is called the difference quotient. The name makes sense because you have a difference in the numerator. A quotient means the answer to a division problem. Well, it is a division problem. We are going to try and find this or simplify this. So when it says find, we're going to, yes, try and find it, but really we're going to try and simplify this expression. We're going to use this difference quotient throughout the year. At the end of the year, you'll see at the beginning of the year how it ties together, and we'll kind of meet full circle from what we do now to what we do at the end of the year. This is kind of an introduction to a little bit of calculus. I'm going to take this step by step. So we're going to first look at this piece right here. I'm going to call that step 1, and I'm going to kind of separate it. So over here, step 1. Whatever's in parentheses is supposed to replace x. In my function, because that's what that means. Go to the function, replace x with whatever's in parentheses. So we're going to go over here and we're going to replace x. So I have x squared. Well, now it becomes x plus h squared. And then it says minus 4 times x. Well, x is x plus h. And then it says plus 7. So I'm going to my function and I'm replacing x. That's exactly what we did in the example above. We went to our function and we replaced r with the number in the parentheses. So I'm replacing x with the number in the parentheses. But now we have to simplify it, so we can't just leave it like this. So the first thing to simplify would be this x plus h quantity squared. Remember, that means there are 2 of them. So if I FOIL that, I would have an x squared, and then I have an xh and an hx. Well, that means there are 2 of them. X times h and h times x would be 2xh. And then h times h is h squared. So I'm FOILing that, x plus h quantity squared. And then I'm distributing. I have a negative 4 with an x and a negative 4 with the h. And then finally we have a plus 7. Now that looks like a pretty big expression. Jack, are there any like terms in that expression?
No.
No, unfortunately there aren't. So this whole first piece here is this answer right here. Now we're going to look at the second piece. We're going to do this part over here, the minus f of x. So this is going to become step 2. Step 2 says minus f of x. That means I'm going to take the equation that represents f of x and subtract it. So I'm going to take a minus, and I'm replacing f of x with its equation. Well, that equation is x squared minus 4x plus 7. Which means I have negative x squared plus 4x and then minus 7. So the last step is to now combine these back into a fraction. So I separated them for us to just be able to look at them as separate pieces. But we're going to take these 2 answers and we're going to combine them back in the fraction. So we really did the part at the top. We've just done the difference part. But we're going to see if we can try and simplify this any further. So we're going to take the 2 and place them together in a big fraction. I'm going to see if I can fit it. So I'm going to take the answers that I just found. And then I'm going to take the second one. So I'm taking those two expressions and I'm placing them back into the fraction. So I separately did the two pieces. I'm taking those answers and throwing them back in fraction form. So it's a lot to look at. So essentially, the two pieces that I found, these two pieces, have made up now my difference quotient. If you look across this huge expression in the numerator, Peter, what do you notice about this expression in the numerator?
They're like terms.
Yeah, which ones are like terms?
The x squared and the 4x and the 7.
That was kind of nice. They all canceled. They were opposites even. So not only were they like terms, but they were opposites. If I carefully write down what's left, I have a 2xh, I have an h squared, and I have a negative 4h. In the denominator, there's still an h. Peter, what do you notice about every term in the numerator?
The h's are being multiplied by something, so you can cancel it out.
I can cancel it out. So the h's in each piece here, I can factor out an h because they all contain an h. And then I can get that h to cancel out. That is the special piece about every single one of these problems that you will do. Our goal is going to be to try and get the h out of the denominator to get it to cancel. So what I'm left with is 2x plus h and then minus 4. This is my remaining simplified expression of the original function, the difference quotient. The last thing that we're going to state is that h cannot be 0. And I need to state that because it was in the denominator originally to start. And eventually we're going to get a number for h. And if that h is 0, then my function is undefined. Questions? So I was hoping to get to example 4 and piecewise functions, but clearly I didn't get that far. I must talk too slow, or it's just the whole fact that learning through a computer takes a little more time than learning in a classroom. So your homework tonight, I believe there are 10 problems where you're evaluating functions. Yes, there's going to be a problem or two like this difference quotient. We will do more of it tomorrow again. So we'll kind of just work through some more problems tomorrow, and we'll continue to work with this difference quotient in the next couple of sections. Questions? All right, have a great day.
Thank you.
Have a good day.
Thank you.
Later. So frustrating.